Okay, so we would start off with introduction of waves. Waves are divided into two types. First type is the progressive waves, and the other type is stationary waves. Stationary waves would be taught in the further lectures. So we would start off with progressive waves. What are progressive waves? So progressive waves are waves which travel or move, and as they move, they transfer energy from one point to another. Progressive waves can be divided into two main categories. First one is the transverse waves, and the second is longitudinal waves. So what are transverse waves? Transverse waves are waves whose direction of vibration is perpendicular to the direction in which the waves travel. So, and all of this is the O-levels concept. So, like if the wave is traveling towards right, then the direction of vibration is perpendicular, meaning up and down. So, forms a 90 degrees, hence it is a perpendicular vibration. And then some examples are example like water waves, waves on a rope, or electromagnetic waves. So this is a basic example of a transverse wave. So like something like this. And it consists of a crest and consists of a trough. So longitudinal waves. Longitudinal waves are waves whose direction of vibration is parallel to the direction in which the waves travel. So something like this. If so the waves would travel towards the right, then the direction of vibration would also be rightwards and leftwards. So in the same direction, and hence they are parallel. So some examples of longitudinal waves are sound waves and waves on a spring. And here is a depiction of how a longitudinal wave looks like. It consists of a compression and consists of a rarefaction. Okay, so we would start off with properties of waves. So the first one is reflection, and the second is the refraction. And these are the topics that were already taught in the O levels. So this would be counted as a assumed knowledge, and we would continue with superposition, interference, and diffraction. And these are the topics in the AS syllabus. So starting off, before moving on to the properties that are the superposition, interference, and diffraction, we need to look at some important terminologies and important points that are in this chapter. So first of all, the path difference. What exactly is the path difference? Path difference basically refers to distance between any two points on a wave measured in terms of wavelength. So for example, if we say like this is point A, this is point B, and they're like 10 meters apart, and then point C, it is 4 meters away from A, something like that. So we say that it is a distance, right? Distance of B from A and C from A, something like that. So the path difference also basically refers to the distance between any two points. So like I said, point A and point B. So any two points, but on a wave, and they are measured in terms of wavelength. So basically, like if we take this crest and a crest, so we know that between crest and a crest is a distance of one wavelength. So one crest relative to another crest, and the distance would be basically one lambda or one wavelength. So one crest and successive trough would be half the wavelength, and one crest and skipping one crest and another crest would be the distance of 2 lambda or 2 wavelengths. So moving on, what is a phase difference? Phase difference is basically the distance between any 2 points on a wave measured either in degrees or in radians. So this basically is like the sine graph or the cosine graph that we make. So a standard sine or cosine graph, we know that it starts from 0 degrees and ends at 360 degrees. So basically one complete wave formation is of a 360-degree angle. And in radians, it would be 2 pi radians. So basically phase difference and path difference only have a single difference, and that is that path difference is measured in terms of wavelength and phase difference is measured in terms of either degrees or radians. So let's say that a crest compared to a crest would be one wavelength apart, or one complete wave. So one complete wave is equals to 360 degrees. So the difference phase difference would be 360 degrees or 2 pi, and a distance between the trough and the crest would be half the wavelength. So half wave means 180 degrees or corresponds to 1 pi radians. So moving on, here is a small pointer, and it just sums up this idea which we just did for this calculation of the phase difference, and that is a path difference of 1 lambda corresponds to a phase difference of 2 pi radians. So we know that a one complete wave has a wavelength of 1 lambda, and one complete sine wave is produced or cosine wave is produced in 360-degree angle. So 1 lambda corresponds to 360 degree of angle. So the path difference of 1 lambda is equal to the phase difference of 2 pi or 360 degrees. So moving on, so basically there are two types of links between points on a wave. So the first one is in phase points, and the other is out of phase points. What are in phase points? In phase points are points, 2 points if upon comparison exhibit the similar behavior. Example: crest with a crest, trough with a trough. So what does this mean? This basically means that they are moving in the same direction and they have the same velocity. So let's say we have a wave. Here's our wave, and here are our two waves. So how do we know that the points are in phase? So the easy way to find out if the points are in phase, or to find out which points would be in phase, is to divide. Like if there are two waves, so just divide the two waves into single unit waves. Like single unit waves means that divide two waves into parts of single waves. So like this is one single wave, this is one single wave. If there are three waves or four waves, then do something like that again. So like break it and break it again. So one single wave and one single wave. Okay, so now you could see that there are four separate distinct waves, and they are exactly the same. So this means that a point on this, let's name it A, B, C, and D. Even though they are consecutive waves, they are joined together, but for the sake of understanding, we have broken these four waves into four separate waves, and they are exactly the same, and they are labeled as A, B, C, and D. So a point on wave A, like on the crest, on the first crest, would be the similar, and the point would be exactly the same as the same point on the same location on wave B, and it would be the same as the same point on the same location on point C, and this would be exactly the same as a point on wave D at this position. And when you would compare these four distinct waves, you could see that these points are on the exact same spot. These points are on the exact same spot. So this means that if the waves are similar and the point is on the same position on the single wave, that is this one complete single wave, so this means that these points would always be in phase, even though point on this wave A is very far away from this point on D. However, they are on the same position on the same type of wave, so still they would be in phase points, and that is the reason why they would exhibit similar behavior. Okay, so in phase points, the phase difference of the in phase points are 2 pi, 2 pi, 4 pi, 6 pi, 8 pi. So what is the logic? The logic is, if you would see that between two consecutive waves, so the difference would be 1 lambda corresponds to 2 pi, 2 pi rad, or 2 pi radians, and a point on wave A, a point on wave C, and the distance is of 2 lambda, so corresponds to 4 radians. And similarly, point A and point D correspond to 3 lambda, and the phase difference will be 6 pi radians. 4 pi radians, and this would be 6 pi radians. Okay, so moving on. In the in-phase points, path difference is 1 lambda, 2 lambda, 3 lambda, and that is already known by the fact that how these waves were compared. So moving on, what are out-of-phase points? Out-of-phase points are the points that upon comparison exhibit exactly the opposite behavior. So this means that they have opposite directions of travel. So let me draw two waves, or one wave will be perfectly fine. And oppositely means like if I compare a crest with a trough and the direction of travel is towards the right, so the next time this point and the on the trough is going to go up and the point on the crest is going to go down. So because they have exactly the opposite behavior, means they travel exactly the opposite, so that is why they behave exactly the opposite, and this is the reason why they are known as out of phase points. Out of phase means upon comparison they exhibit completely opposite behavior. So as you could see that the phase difference between this will be that of a half of wavelength. So this corresponds to a phase difference of 180 degrees or pi radians. And consecutive out of phase points have a phase difference of pi, 3 pi, if you are going consecutively, like one crest compared to the consecutive trough, or one crest compared to a trough that comes after the first trough. So that would be 3 pi, and then so on and so forth, 5 pi and 7 pi. And out of phase points, path difference is half lambda in this case, and one example could be of 3 upon 2 lambda or 1.5 lambda is comparing a crest, leaving this trough and comparing it with this trough. So dividing it into 3 equal parts, it would be crest to trough half lambda plus trough to crest half lambda plus crest to trough half lambda. That makes it 3 upon 2 lambda. So it matches with this. And so on and so on. If we continue, then it will be 5 upon 2, 7 upon 2, 9 upon 2, so on and so forth. So there are some wave terms that you are required to know for the examinations and must have an idea of what they mean. So, and if you want to note down these terms, you could pause the video and note it down or take screenshots. Whichever way is easier for you, you could go with that. So, amplitude, it is defined as the maximum displacement of a particle in the wave. So taking an example of a transverse wave, so let's say this is the amplitude. So the maximum displacement, as you could see, of this point is over here, so this would be the amplitude of this specific particle. So amplitude again is defined as the maximum displacement of a particle in the wave. Then comes the phase difference. We have already discussed previously. Again, it refers to distance between any two points on a wave measured in terms of degrees or in radians. Path difference was again discussed earlier. So it refers to the distance between any two points on a wave measured in terms of wavelength or lambda. And exactly what is wavelength? Wavelength is the shortest distance between any two crests, between any two troughs, or between any two points in phase. What is a time period? Time for a particle in the wave to complete one vibration. So after one complete vibration is finished, so the time taken for the particle to complete that is known as the time period. What is the frequency? Frequency is basically number of complete vibrations per unit time, or number of complete vibrations per second, and the units of time period is seconds. The units of frequency is 1 upon seconds or hertz. Moving on, what is displacement? Displacement is the distance of a point on the wave from its undisturbed position or equilibrium position or mean position. So distance or displacement and amplitude. Amplitude is the maximum displacement from the mean position, and displacement is just any displacement. So if this is a wave, so this is also some displacement, even though not the maximum, this would be the maximum, but still this is also some displacement from the mean undisturbed or equilibrium position. What is the wave speed? Wave speed is the energy with which energy is transmitted by a wave. So these are some terms that are required by the examiner, that you must know these and must have an idea of what they basically mean. So let's continue with the equations of v equals to f lambda, how this equation v equals to f lambda is derived, and what's the logic behind it. So we know that speed equals to distance upon time, or velocity equals to displacement upon time. In waves, the distances are basically wavelengths, are measured in terms of wavelengths, like lambda, half lambda, 1 upon 2 lambda, 3 upon 2 lambda. And the time period is measured in terms of t, or the time which the wave takes to complete, which a particle of a wave takes to complete one complete vibration. And we know that frequency is inverse of the time period. So keeping in mind this formula that speed equals to distance upon time, so it means that speed equals to distance into 1 upon time. Distance could be replaced by the term lambda, and time could be replaced by frequency, because we are talking about the inverse of time. So inverse of time is equals to frequency. So it could be replaced by frequency, and the formula becomes v equals to frequency into the lambda, or the wavelength of the wave. Moving on, concept of energy in waves. In progressive waves, the particles which make up the material through which the wave is traveling do not move along. As you could see, and you already know, that if this is a wave traveling, then there is only the vibration of particles. And let's say at another instant, the wave is in this position. So we know that the particles are only moving up and down, and they're not traveling in the direction of the wave motion. So, keeping this in mind, we come to a conclusion that it is just the energy that is transmitted by the wave. So, how exactly is this happening? Basically, when each particle vibrates, that is, like if this is a wave, and here is a particle at this point that is vibrating, and at another instant the wave will be something like this. So the particle is going to go down. So it's vibrating up and down. So when each particle vibrates, as it does so, it pushes its neighbor, which pushes its neighbor. So basically, it is a sort of a chain effect, that when it vibrates, the other particle vibrates, then the other, and so on. There are particles and particles that vibrate, and they form a wave pattern, and like this, the energy is transferred from one particle to another particle. Then we will come on to the concept of intensity in waves. Intensity of a wave is defined as the rate of energy transmitted per unit area. So a rate of energy is also known as power, or so we could also say power per unit area. And the units of intensity are power, that is watt, cross-sectional area, that is meter square. So watt upon meter square, or watt per meter square. So the relation between intensity of a wave and its amplitude, or distance from the observer. Intensity is known to be directly proportional to the square of the amplitude of the wave, and is known to be inversely proportional to the distance squared. So if we just remove the proportional sign, then we would replace it by a constant. So the equation of intensity becomes constant times amplitude squared, or constant divided by the distance squared.